Okay, let's get started. So today's topic is from denormalization to joins, why ClickHouse cannot keep up, right? So we're gonna talk a lot about joins and a lot of like comparison between different open source real-time OLAP databases, right? And I'm Sida Shen. Welcome everyone. So first, let's go over the agenda, right? So first, we're gonna talk about data modeling and what is denormalization and why on-the-fly join is superior than denormalization and the problems that's associated with denormalization, right? And then we're gonna go to some case studies of some of the industry leaders, including Airbnb and Tencent, about how they are ditching denormalization and creating a more streamlined uh, analytics framework, analytics pipeline, right? And then we're gonna go into some technical stuff, right? We're gonna talk about why ClickHouse struggles on the fly joins, and we're gonna do a kind of like a deeper technical comparison between ClickHouse and other open source solutions on query planning and distributed computer architecture and query execution, right? And the technical comparison is not gonna be very detailed. They're all gonna be on the architecture level, right? And first, let's talk about data modeling and what kind of data models are there, right? And here you have, must have seen this before, flat table schema, star schema, and snowflake schema, right? And flat table schema is like a single table schema, right? Where you put all of your data in a big flat table, where star and snowflake schema are multi-table schema, right? So they're relational. So you have multiple tables and the tables relates to each other on some column or on some key, right? Um, and the process of denormalization is that uh, normalization is normalization is for going from your flat table schema to your snowflake schema, and denormalization is the other way around, right? Normalization has been the best practice for database management systems since the relational database was invented. That's like almost 50 years ago, right? It does a lot of good stuff. So it eliminates redundant data and actually simplifies the query process for you. So you don't have to look at a 2000 column table and try to write a query for that, right? So overall, it improves your workflow, right? But recently in OLAP, especially in real-time OLAP, because join operation is essentially is expensive, and a lot of the data vendors or the database vendors just choose not to optimize it, and depends on actually the user to perform a denormalization. So going from a snowflake or star schema, multi-table schema, back to a flat table schema to avoid the join queries. And this is actually a pretty harmful thing to do and creates a lot of problems. So the cost of denormalization, right? It's not only the compute or the more data you store. Let's take a look at an example here, right? Here on the left, you can see we have a customer table, and on the right, we have a order table, right? And the customer ID are in both tables, and that's the key that's gonna relate the two tables together, right? And okay, say a data engineer wants to build a dashboard out of that, right? And he doesn't want to write a join query because the underlying database cannot handle it, whatever the one he's using, right? So he denormalize the two tables into a flat table on the customer ID key, right? Big flat table. But what if, okay, so someday your security team comes over and say, okay, hey, your customer name cannot be just your name. You have to somehow mask it, right? And you want to change your alias to some other hashed value or something that's not Alice, right? Um, there creates a problem, right? Not only does the data engineer needs to change the source, which is the two tables, But the denormalization pipeline as well needs to be reconfigured, as well as the flat table. The whole customer name column needs to be backfilled, right? What seems to be a simple change, right? A change of a metric or a column. But technically, with denormalization, it creates a lot more problem, right? So denormalization actually logs data into a single view format, so it has no flexibility to adapt to any business change, right? So in this case, you are backfilling one column. Let's say you have 1 million or even 100 million rows of data. That's probably okay, right? But keep in mind, the customer table can be 100K, but this order table can be, in the billions or hundreds of billions of rows. And backfilling this is much more expensive than you think. Okay, so denormalization not only makes your analytics rigid and not able to adapt to business changes, it's also very complex, right? Especially in real-time data analytics. So with real-time data analytics, tight time constraint, so you cannot really use something like Spark or those batch analytics tools. So you need to go for those stream processing tools and write stateful stream processing jobs, right? Which is known to be difficult to use, requires a lot of technical expertise and a significant amount of engineering skill, right? And those stream processing tools oftentimes they don't even take SQL. You need to write actual code to use them efficiently, right? So yeah, denormalization makes real-time data pipeline really expensive. So what is the solution? So the solution is actually simple, right? Just make join run faster. So we don't do denormalization anymore. We keep the same data schema between the your data source and your serving layer, right? So no table schemas change. So here I want to kind of introduce StarRocks. So it's the real-time OLAP database that we're going to use to compare to ClickHouse in today's webinar, right? Some short introduction. So it's cloud native, it's storage and compute separated design, and supports real-time mutable data. So you can perform fresh data updates with StarRocks, right? And also has no external dependencies, so it's easy to maintain, as well as it's SQL compliant. So you can connect whatever BI tools or applications you have that's also SQL compliant, standard SQL compliant, and it's gonna work, right? But the one thing that I can count StarRocks on is the StarRocks ability to perform really efficient join queries. So from looking at our users' use cases, StarRocks join is actually fast enough that you can ditch the majority, or for a lot of users, all of their denormalization pipelines, even with large scale of data and with high concurrency, right? And first, let's look at some benchmark data. So this is the SSB dataset. So there's actually two variants of this SSB dataset. So the original SSB dataset is multi-table, so it has, I think, 5 tables. And ClickHouse actually created a variant. So we call it SSB flat. So basically, what engineers at ClickHouse did was pre-join all of the table into a flat table and run the same queries, but without the join part, right? And let's look at some results. So StarRocks, ClickHouse, and Apache Druid. So the first 3 are ran on the flat schema, so no joins involved. And say StarRocks is the fastest, and ClickHouse comes second, and Druid, fortunately, comes last, right? But the interesting part is the last, the blue one, right? So this is actually StarRocks running on the multi-table schema test. So you can see that StarRocks multi-table performance is actually faster than Druid's single table performance, and it's almost as fast as ClickHouse single table performance, right? So StarRocks multi-table join performance. So you can think of like, if you're using ClickHouse or Druid, you can just ditch your denormalization pipeline and actually without losing much performance, right? And StarRocks is those MPP databases are designed to scale, so you can actually deploy whatever you're spending on your denormalization pipeline and deploy that into more StarRocks nodes. It's gonna even run faster, right? And it's gonna give you the flexibility, right? And this is just showcase some performance numbers. And here, just for the fun of it, let's take a look at TPC-DS, right? SSB benchmark, you can see that as a resembles more of a dashboard or a customer-facing analytics kind of scenario where the query is not insanely complicated. Resembles those the queries are generated by some kind of application or front end, right? But TPC-DS is more like those ad hoc, really complex ad hoc queries, and those ETL queries, right? So a lot of really heavy joins and high cardinality aggregations, right? And StarRocks versus Trino. Trino is a query layer or query engine on the data lake that's really good at doing joins, really doing complex joins, right? And StarRocks even 5.5 times faster than Trino on TPC-DS, querying the same data on the data lake, right? So now let's take a look at some use cases. So Minerva is Airbnb's own metric platform. It holds around like 6 petabytes of data. So before they were using Apache Druid and Presto as their kind of real-time OLAP database and the query engine, right? Because Druid is not really known for its join, actually cannot really do join. So they needed to denormalize everything, and that creates a lot of problem, right? First is the flexibility problem. So adding or changing a metric can take hours or up to days because of the reconfiguring of the pipeline data pipeline, as well as backfilling the data, right? And also, this is a huge waste for storage because they're denormalizing, they're creating white tables that's really getting used. And creating those flat tables also costs a lot of hardware resource, a lot of CPU and memory, right? And then they found StarRocks, right? Because StarRocks can actually do join on the fly really well. So the biggest change for them going from Druid plus Presto to StarRocks is that, of course, the architecture is simpler, right, from 2 to 1. But the bigger change is that denormalization is not default anymore. It's only done on demand, right? So last time we checked, there's only like 20% of the table that are still denormalized, requires high concurrency or very low latency, and majority of the tables are normalized now. It saved them a lot of time and money. And the second case I want to kind of talk about is Tencent Games. So Tencent Games has a little different story, right? So before they were using even earlier technology like Postgres and MySQL for serving. And not only those two cannot do join, they cannot really do on-the-fly aggregation as well, right? So they had to pre-compute everything, including joins and aggregations. And this create a problem because whatever analytics you do, you need to create a pipeline for that first. So you cannot really do any multi-dimensional kind of self-service analytics workload, right? And also they're running into problem for maintenance of the whole cluster because there are actually two different pipelines for real-time and batch, and that's really complex and expensive for them to maintain, right? And after moving to StarRocks, they kind of unified everything into StarRocks, right? Because StarRocks can not only do aggregations on the fly really fast, it can also do joins on the fly. So there's no more waiting for the pipeline to finish or wait for the pre-aggregation to finish, right? So analysts can just go and do multi-dimensional analysis kind of self-service in a self-service fashion, right? And also simplified architecture. So just exactly why ClickHouse cannot do join, but StarRocks can. StarRocks and other similar open source solutions can, right? So here we're gonna go into some technical, architectural, like technical discussions about how a query work, right? So when you write a query, this is similar for every database out there. So this is really high level. So you write a query and it first hits the network layer, right? And it gets parsed and gets sent into the planner. And the planner creates a physical distributed plan that's your underlying execution engine is going to take. And according to the plan, it's going to scan the data from your storage layer, right? And scan the data and do the execution and return the result back to the network layer, right? And there are actually two parts that are very important. So first is a planner. So a good plan is like going from point A to point B, the route you take, right? It doesn't matter how fast your execution engine is. If the route is wrong, there's no way you're gonna get a good query latency out of that, right? And the second is how you compute. So the execution engine and architecturally, does it support using all of the CPU cores from your whole cluster, right? And that's important as well. And we're gonna break that down and do a comparison. And first, let's take a look at query planning and what it takes to generate a good query execution plan, right? And here is a more higher level illustration of how a query planning works. So first, your SQL query hits a parser, and a syntax tree is generated, right? And the transformer and generates a logical plan, right? And your optimizer from the logical plan generates a physical plan, right? And here, the real optimization happens from the logical plan to the physical plan, right? The reason being, the logical plan is actually what your SQL is trying to do. So is, let's say, join A, join B on the key, right? And there's really not much you can change, right? There's really not much you can optimize. But a physical plan is how your database actually executes this query on a single node or distributedly, right? And so the optimizer is a key of to fast query, and especially for joins, right? Because there are many ways a join can be executed, right? Different tables, the tables can be reordered, right? And you can select different join algorithms, and you can select different join strategies, distributed join strategies, or or other advanced features like runtime filter pushdown. And I'm gonna go into those details later. But the search space is enormous, and the difference between an optimized plan and an unoptimized plan can be several order of magnitude difference. And ClickHouse Planner uses a rule-based optimizer, right? It makes decision based on only on predefined sets of rules or heuristics, right? It has little consideration for the actual data distribution or the current database state. It probably knows like the tablet, like the file size or how many rows, but that's about it. No consideration for the distribution of the data, like the min max or histogram, right? And it's really nothing wrong with a rule-based optimizer, if you're not really doing complex query. So it really works for simple databases, but not really for those OLAP workloads. And so when you're using ClickHouse, if you're a ClickHouse user, right, when you write a query, oftentimes it requires you to write the hints with the query, like what join algorithm to use, and requires you to like order the table in the right way so it runs the fastest, right? But in comparison, StarRocks use a cost-based optimizer, and that's the first key differentiation for efficient join operation, right? So the cost-based optimizer actually collects statistics and estimates the cost of each plan and use a greedy algorithm to select the best one, right? Um, StarRocks' own cost-based optimizer is natively built and is deeply integrated with the execution and the storage layer, right? And it's something about building a optimizer is that it's really deeply coupled with your system. It's different for every execution engine. It's different for every storage engine. So it has to be natively built, and it's almost impossible to get right on the first try. And thank God StarRocks is open source, so we could iterate that with the community, and it took us like a year or two to get it right. And this is the main reason why StarRocks is the query is efficient. And also StarRocks has a lot more other kind of optimizations, right? Like data pruning. So the objective of this is basically to minimize the amount of data that's being processed by your CPU. So let's consider this query, right? Select star from fact, join dimension table. Fact of dimension ID, dimension ID, dimension.id, right? Where dimension.price is greater than 100, right? And so let's say the fact table has a billion rows and scans a billion rows, and the dimension table scans 1,000 rows, right? So what if we can send this predicate to the fact table, and it can save a lot of the data that's being scanned, right? So it can possibly go from a billion to a million. But there's more than that. So this predicate, this column might not even exist in the fact table, right? So simply sending the predicate itself over, it's not going to work, right? So what StarRocks does is it has the option to send a Bloom filter from the dimension table, so the right table to the left table, right? And thus still do this 1 billion to 1 million row optimization, right? But this is a little more complex than just that, because sending this Bloom filter over has its cost as well, right? Is the cost of sending the Bloom filter worth it? Uh, that's a question that our cost-based optimizer needs to answer, right? So is the filter worth the network cost? Probably yes, probably a no. Right? And this is something we've optimized for a very long time. Okay, and now let's talk about query planning, and now let's talk about compute architecture and how does that affect join operations, right? And first, I want to kind of go over some key concepts so we don't get confused, right? And first, there are some join types: inner join, outer join, cross join, semi join, or as of join. And those are logical views of a join. Those are the SQL or the SQL function that the user writes that describe what they want, right? And then we have join algorithms, right? You probably heard of that. Hash join, parallel hash join, or merge sort join, or yeah, there's many more. And this is actually how a join is executed on a single node, right? This is only on a single node. And there are join strategies, and this is the key. And you can have a single instance join, like a local join. We call it a local join. We can do a collocated join, broadcast join, shuffle join, and this is all on a network level, right? So this is really single node versus distributed, and the strategy of distributed joins, right? And here I want to ask you a question. So does your workload or your OLAP workload fit in one node? The answer is probably no, right? And a join happens to be the most or one of the most expensive operation you can write with a SQL query, right? So if your answer is No? Then we need to focus on the join strategies, because all of the others, especially the join algorithms, only associate with one node, right? And the join strategy is the one we're going to focus on in this section. So just exactly how to execute joins at scale with many instances. So single node join is very different than distributed join. Distributed join operation, one thing needs to do is that make sure all of the worker nodes gets the right data that it can work on, right? So it tries to minimize, during the process of distributing the data, it tries to minimize the network utilization. So that's the amount of data that's being transferred between nodes. And it tries to minimize the memory utilization, right? And that's the amount of data that's being processed in memory. You don't want the same data that's being copied everywhere, but you don't get multiple of performance, right? And here I want to introduce something as called data shuffling, right? And so why does it matter so much for joins? I'm going to use the next 4 or 5 slides to talk about that, right? Data shuffling is basically shuffle the data to all of the worker nodes based on a join key, right? Based on the key, shuffle all the data to the right nodes. So you can shuffle any table, like your left table or the right table, right? And this is a key to truly scalable distributed join. I'm going to use some examples like shuffle join, broadcast join, bucket shuffle join, and some other like localized or single node join to demonstrate this, right? And first, let's talk about some different join strategies, right? And the first type is kind of like, say, local join, kind of made this word up, versus distributed join, right? And local join, you can think of them as a single node join, right? And to use multiple nodes to process a query, with a local join, it requires a certain data distribution, right? So you first have to organize your data in a certain way for the join to work on multiple nodes, right? And distributed join actually sends the data on the fly during the join query execution, right? And first, let's look at the first local join. So first is collocated join, right? So this kind of join doesn't really send data, so it relies on the both tables to be distributed on the same join key. So if you want to use like collocated join, you need to know about the query, at least about the query, the join condition beforehand, right? And the join is done completely locally, so there's no network overhead. It's very fast, but it's not flexible at all, right? Because you need prior knowledge of the query before actually ingesting the data, right? And this does not require any data shuffling. And the second one is a distributed join. It's called broadcast join. It also does not require data shuffling, but it has many shortcomings, right? So what it does is that you have a left table that's, so assume it's a bigger table, and you have a right table, and that's a smaller table, right? So it broadcasts a copy of the smaller table to all of your worker nodes. So let's say we have 3 nodes, right? And the right table is 1,000 rows. So the network overhead is actually 3,000. It scales not only with the size of your data, but it also scales with the size of your cluster. And that's very expensive. And the right table needs to fit into every single one of your worker node, or else it's not going to work, right? And this type is only suitable for small clusters or cost effective for small clusters, or joins with a very tiny right table, right? And this is actually the only kind of distributed join ClickHouse can support, because it doesn't really do data shuffling, right? And then let's talk about shuffle join. So shuffle join shuffles the data between the both tables to all of the nodes based on the join key, right? Say if you have 200 nodes, the number, the data that's being transferred in the network and that's being processed in memory it's still 5,000 rows and 1,000 row, right? So it's very scalable. So the more nodes you add, the more performance you're gonna get, and you use the same amount of memory if you want to run the same query, right? It does not scale with the size of the cluster, and this is the key of achieving truly scalable join, uh, like in a distributed fashion, right? And StarRocks also has other optimizations. Like for example, we support bucket shuffle join, right? So if the join key already aligns with the distributed key of the left table, we can only shuffle the right table. So it's much cheaper, right, on the network. So it's automatic and doesn't require any more configuration, right? But the ability to perform shuffling is the key here, right? And let's take a look at what we just talked about, right? Broadcast join, shuffle join, bucket shuffle join, collocated join. Oh, and replicated join. Replicated join is actually um, just pre-computed broadcast join. So you just during data ingestion, you just replicate the right table into every one of your node. So basically, use your hard disk, right? So replicate the tables without without the ability to do data shuffling. The only option that ClickHouse has is that either first you have to know about your query pattern beforehand, and your data distribution needs to based on that, so that you can do a collocated join or replicated join, right? Or you can do a broadcast join where the right table needs to be very small, right? And any other scenario, if you want to join two like billion or hundreds of billion scale table together, both are big, they're not going to work, right? You need shuffle operation because it's going to bottleneck on the size of its single node, right? Okay. And now let's talk about computer architecture. We talk a lot about how a query is executed, both on a single node and in the distributed fashion, right? And here is more like general theory about the computer architecture, right? So the first type is scatter gather. So you have some kind of a leader node and has some kind of task, and it distribute to all of the nodes, all of the follower nodes, and they do the computation and aggregates the result back to the bigger leader node, and the leader node does the final calculation, right? And this is the architecture that ClickHouse follows, and is really easily bottlenecks on a single node, right? And then you have those stage by stage or map reduce kind of architecture, right? It supports data shuffling, so it can do this shuffle and do the computation and shuffle again, right? But each one of the shuffle or the map and reduce process needs to be persisted on disk. So their wait time before a task, right? It's very stable. It's very suitable for those like long running ETL jobs, but is just not ideal for low latency queries, right? For these, you can take a look at Spark or its Photon engine, Databricks Photon engine. It follows this kind of compute architecture, right? And then you have those pure in-memory MPPs, right? It supports data shuffling and data shuffling between the memories of your worker nodes, right? So it's zero wait time, and it streamlines the execution, and it's great for sub-second joins and high cardinality aggregation at scale, right? And let's take a look at StarRocks architecture, right? Let's go back to this image. It features a storage and compute separated design. So talk about MPP. This is one thing I kind of want to debunk, is that I see a lot of people online that say MPP means storage and compute coupled design. And that's actually no. MPP actually means you can shuffle your data and scale your workload or scale your query latency with adding more nodes, right? It does not mean coupled storage and compute. Actually, StarRocks has a decoupled uh, storage and compute design, right? And StarRocks supports data shuffling, does many distributed join strategies. So it's very great for low latency, large scale joins and aggregations, right? And also has the option to go pure in memory for data shuffling. And so it's great for sub-second query. Okay, let's do some conclusion. So StarRocks versus ClickHouse. So on-the-fly join versus complex and rigid denormalization data pipelines, right? And for query planning, and StarRocks has a cost-based optimizer versus ClickHouse has a rule-based optimizer, right? And StarRocks also built a lot more optimizations specifically for joins, like the global runtime filter we just talked about. Actually, if you're interested in the global runtime filter, you can go to the Seller Data YouTube channel. There is a Go pipeline free webinar with DBTA, and there I did a demo of how the global runtime filter works. Right, that's really fun. And for the compute architecture, StarRocks can do data shuffling, and ClickHouse cannot. So StarRocks can support all kinds of joins. Big table join small table, big table join big table, 5 big tables join together, and StarRocks can handle them. But ClickHouse cannot because of the architectural design, right? Okay, so that's all I have, and you can check out the Seller Data blog, sign up Seller Data Cloud for a 30-day free trial. You can join our Slack channel and give us a star on GitHub, the StarRocks open source, real-time open source OLAP database project. And also you can connect with me on LinkedIn. Just type in myname.com. It's going to take you to my LinkedIn page, right? Here, is there any question? How there is one question, how different the query optimizer, including join, from Spark optimizer? Was there any motivation from other optimizers while building in StarRocks? That actually, yes. We actually followed a paper. I'm gonna send the paper to you in a bit. And StarRocks actually it's a little different than Spark. It's built for very different purposes. So Spark is really built for like ETL workloads, and StarRocks is really built for those like low latency uh, queries. So it's like stage by stage versus like pure in memory, right? So the query optimizer is actually quite different. I'm gonna send you the paper afterward. Are you in our Slack channel by any chance? If it's yes, I'll search up your name. Okay. And let's see if there's any other question. Why do I see ClickHouse outperform StarRocks on ClickBench, and when your data say otherwise? Okay, yeah. Let's talk about that. Let's talk about the ClickBench benchmark. So the reason is the default view of ClickBench is actually tuned, includes all of the tuned performances, and ClickHouse actually their tuned benchmark result. Actually, they changed they even changed the SQL query, so that's not really fair. So if you turn off the tune button, you're gonna see us first. If the internal storage and the compute node is decoupled, doesn't it increase the network overhead? What is the recommended design? Yes, it does. So for us, so if you persist your data in a remote storage like a S3 object storage, you can always build cache, right? And StarRocks actually has a data cache that caches remote data on that's persisted in remote data. into the local disk as well as in memory. It's multi-layered, right? So the data that's being cached locally is only there for uh, to accelerate the query performance, so it doesn't persist. So you can still dump the entire thing and not lose any data, right? And StarRocks also has the materialized view feature, right? So you can take external. Oh, that's for data lakes, right? So you can take like data from your iceberg table, and you build a materialized view, and the materialized view is actually a table that's hosted with our internal storage. So that way you can bring the data in, and there are many ways to accelerate. Can you speak to the join algorithms and strategies of each database? You have talked about ClickHouse and Databricks a bit. I'm curious about how StarRocks compares to Snowflake, Oracle, MySQL, Postgres, and SingleStore. Okay, this is good. So Snowflake and SingleStore cannot really give a lot of insight because they're not really open source, and I don't really know the internal how they works. But Snowflake, I think Snowflake operates similar than what we do, right? That's another question. Sorry. Yeah, it's a little similar than what we do just by looking at the query profile of theirs, right? Um, they have operators billing, and we have operators billing as well. So they do shuffling, pure in-memory shuffling, and so their architecture is a little similar than ours. And for MySQL or Postgre, those are like role store database. So they're not really designed to do OLAP workload, and I'm not even sure if MySQL has a cost-based optimizer or yeah, but they're not really designed for OLAP workload, right? So all of the OLAP database that we talk about, like ClickHouse, StarRocks, or even Druid, they're all columnar store, right? So by storing data in a columnar format, so it's better for OLAP workload, right? You're always taking data big chunks by column. You're not updating like row by row, like for transactional databases, right? So that way we're way faster than MySQL or Postgre. You can actually check out the ClickBench uh, benchmark test, and that's actually a single table test. But we're many times, or all of the OLAP databases are many times faster than the columnar store ones, are much faster than the row store ones. And Tyler's question, I think, already answered. Um, let's see, is there any other question? Oh, there is one. Are there any drawbacks with shuffle join? We'll say yes. There's no like one strategy that works for every single scenario, right? Shuffle join actually shuffles the both of the if you have two tables, a bigger one and a smaller one, actually shuffles both ones um together. So if your right table is super small, and sometimes a broadcast join is more efficient, right? So it doesn't work in all scenarios. It's another question. Where can I get the performance benchmarks? So you can go to sellerdata.com and look at the let me see. Um, you can go to sellerdata.com and under resources, and you can go to white papers and case studies, and the first one is the performance benchmark comparison. Is there active development work for improving StarRocks drawings, and more generally, the optimizer. What enhancements are being worked on? So, yeah, so the foundation is already being built, and a lot of the optimization that we're doing right now are basically solving a lot of the bad cases we see in the field. Or if you're a lot of the Slack users, they're heavy StarRocks users, and they come to us, and a say a query is slow, and we take a look if our optimizer is doing something funny. And that's that, right? And recently we did a lot of optimization on string. So if you're drawing on the string column, especially on the data lake, external data storage, uh, and we have uh, optimized that a lot in this past 2 months. Okay, we're about time. Is there any other question? Okay, I think that's it. Thank you everyone for joining. I hope you had a good time. If you have any question, please any additional question, please raise them in our Slack channel, and I'll keep an eye on them. Right? Okay. Thank you. See you in the next one.